again for the second part of rate law. So what you are going to learn? So first, you are going to learn write rate law with respect to the order of fraction. Okay, and then write the integrated rate equation for the 0, first and second order fraction. Okay, and then perform calculation. Okay, perform calculation using the integrated rate equations. Alright, so we move to 0 order fraction. So consider the fraction. We have A is the return decomposed to produce product. Therefore, the rate law is rate equal to K concentration A power of X. For the rate law, for the 0 order, okay, the fraction is independent of the concentration of return, which means that rate for 0 order does not depend on the concentration of the return. So therefore, the rate law for 0 order is rate is equals to K concentration of A power of 0. So anything power of 0 is equals to 1. So therefore rate is equals to K. Right? So when we substitute unit of rate, that is molar per times, into the rate law for 0 order, we'll get molar per time is equals to K times 1. Times 1 here because concentration of A power of 0, anything power of 0, it become 1. So therefore, the unit of K for 0 order is molar per time. So when we plot a graph of rate versus concentration of A, so we get constant line here. So because rate is equals to K. Alright, next. Okay, by using calculus, okay, we integrate both sides, rate and also K concentration A naught. So we will get this following expression. Concentration A naught minus concentration A equals to KT. So this expression is referred to the integrated rate law for the 0 order, where A naught, concentration A naught is referred to the initial concentration of A. Concentration A is referred to the concentration A remain after given T. And K, we already know that K is rate constant. So we plot a graph. Okay, so we get two graphs. Right, so if concentration A naught minus A versus time. So we will get a linear graph start from the origin. Why? Because this is referred to the y-axis. Okay, and K here is referred to the M, gradient of the graph, and T is referred to the X. So this is graph of y equals to mx. So a linear graph start from the origin. Okay, positive linear graph. Okay, so if we switch, the concentration of A become the y-axis and time is referred to the x-axis. So we will get a negative linear graph because concentration A here is referred to y. Okay, and negative K is referred to negative M, which refer to the gradient of the graph. Okay, T here is referred to x plus concentration A naught here is referred to C. So this is referred to C, which referred initial concentration here, A naught here is referred to C. So we will get negative linear graph. Alright, next half-life. Okay, so when we substitute, T is equals to T half and concentration A is equals to concentration naught over 2 into the integrated rate law. Okay, we'll get this expression. T is equals to concentration A naught over 2K. Alright, so when plot a graph, concentration A versus time. So for 0 order, so the graph will become negative linear graph. Okay, like this. So start with this one is referred to the initial concentration A naught with negative gradient. Okay, example 1. So for the 0 order decomposition of ammonia and on tungsten, so we have ammonia gas decomposed into nitrogen gas and hydrogen gas. The rate constant is 2.08 times 10 power negative 4 molar per second, what is the half-life, okay, of a 0.25 molar solution of ammonia? How that we can answer? So first you have to use the formula of half-life. So T half is equals to concentration A naught over 2K, and then you have to define what is A. So A is refer to the ammonia. So write in the formula. Initial concentration of ammonia is refer to the 0.25 molar. Just substitute in the formula, and then and also the value of K, that is 2.08 times 10 power negative 4. Then you get the value of half-life is 601 seconds. Alright, next, how long? Okay, how long is refer to the time. Okay, will it take for the concentration of ammonia to drop from 1.25 molar to 0.388 molar? Right, so therefore this is referred to the initial concentration of ammonia. So, and this is the concentration of ammonia at T time, in that T that we want to calculate. So you have to use the integrated rate law. Okay, since given there are differences in the concentration of the reactant. Okay, right, substitute the values. So initial concentration of ammonia 1.25, and concentration of ammonia at T is referred to 0.388 molar. And also substitute the value of K. So you get the time taken, okay, for the ammonia to drop is 4.14 times 10 power of 3 second. So example number 2, okay, the decomposition of ammonia on tungsten at 1100 degree of Celsius 0 order fraction with the correct constant is 2.5 times 10 power 4 molar per minute. The reaction equation is as follows. What is the half-life of the reaction when ammonia is 0.75 molar? Okay, so you have to write the formula. So then forget to convert the concentration of A naught here with concentration of ammonia naught. Okay, substitute the initial concentration which refer to 0.75 and also the value of K, right? So you get the half-life of the reaction is 1.5 times 10 power of 3 minutes. Okay, can cancel molar with molar. Right, so next, how fast? How fast is a 0.75 molar of ammonia being changed to nitrogen and hydrogen? So how fast here is referred to the rate. Okay, so which means that for question B, you have to apply the rate law for the zero order. So rate is equals to K. So and then you just substitute the value of K. So this is the rate for the ammonia. Okay, alright. Okay, so for first order reaction, consider the following reaction. So we have A is the reactant produced product. Rate is equal to K, concentration of A power of X. So for the rate law, rate is depend on the concentration of the reactant raised to the sum power. Okay, sum power here is equal to the first power. So rate is equal to K, concentration A power of 1. So when we substitute the unit of rate, that is molar per time, is equals to K, and then unit of concentration of A is equal to molar. So therefore we cancel out the unit of molar. So unit of K for the first order is per time. Right, so when we draw a graph of rate versus concentration of A, then we get a straight line graph start from the origin. Why? Because rate here is referred to the y-axis. K here is referred to the gradient. Okay, gradient, rate constant is referred to the gradient. And concentration A is referred to the x. So the graph here is graph y equal to mx. Right, so next, by using calculus, when we integrate both sides, okay, we will get this expression. Okay, ln A naught over concentration A equals to KT. So A naught here is referred to initial concentration of A, and concentration A remain after T, given T. And K is referred to the rate constant. Right, so there are two kind of graph that sometimes related to the integrated rate law. So the first graph here, if we plot ln concentration A naught over concentration A versus time. So where ln concentration A naught over concentration A is referred to y-axis equals to K is referred to the M, and T time is referred to the X. So this graph is y equals to mx. So that's why we get a linear graph start from the origin. Okay. So for the second graph, if we plot ln A versus time, where ln A here is referred to y equals to negative K is referred to negative M, T here is referred to X, plus ln concentration A naught, that's referred to C. So this is C. So that's why we get linear graph with negative gradient. Okay. Alright, next half-life, when we substitute T half equals to T half, and concentration A is equals to concentration A naught over 2 into the integrated rate law. Okay, so we get like this. Okay, this expression T half equals to ln 2 over K. So when we plot a graph of concentration versus time for the half-life, so we get a curve graph, okay, like this. Look at the trend. This is the initial concentration. Let's say A naught. The half of the concentration of A is right here, somewhere here, half. And the time taken, and read the time here. So this is referred to the first T half. Let's say it takes time 5 minutes. And then for the second T half, half of it here. So we get second T half. That is also 5 minutes. We look at the trend. Third half life also we get 5. So the trend here we find out the trend here is constant. So for each of the half life, this shows that the reaction is first order. Okay. Right, we move to the example. Alright, so example 3, the decomposition of N2O5 at 45 degrees Celsius is a first order reaction. Write the rate equation for the reaction. So rate equation is referred to the rate law. Alright, so in already given first order. So we can write rate equals to K concentration N2O5 power of 1. So you cannot write like this. This is wrong. If you answer general like this, so this is wrong. Because the reactant is already given in the question, which refer to N2O5. Alright, next, calculate the rate constant K, the value of K, if the initial concentration of N2O5 is 1.5 times 10 to the negative 3 molar, and it decline at the rate of 8.6. So this is rate. So how that we can answer this question? So by using the rate law, okay, right? So rate equals to K concentration N2O5. So we can substitute the value of rate and also the value of the initial concentration. Alright, so then we will find out the value of K, that is 5.733 times 10 power negative 4 molar per second. Right? Okay, example number 4. So the decomposition of SO2Cl2 is a first order reaction. Okay, write the rate differential equation. So for the reaction. Okay, calculate the value of the rate constant K at 500 K if 5% of SO2Cl2 decompose in 6.75 minutes. Right. Okay, and then specify the half-life for the decomposition reaction. So we try to answer the first one A, write the rate differential equation. Right, since all here is in gas phase, So you can also use the terms partial pressure. For example, rate is equals to negative D partial pressure of SO2 Cl2 over dt, since the reactant are in gas. So negative because reactant decrease. So equals to positive D partial pressure SO2 over dt, positive because product will increase with time, is equals to positive D partial pressure of Cl2 over T. So instead of concentration, you can also write the rate differential equation by using the terms of partial pressure. Okay, for B, so it's involve the time, and then you want to calculate the value of K, and then given to you if 5% of SO2 as Cl2 decompose. 5%. So 5% here is refer to the initial concentration. So which refer to initial concentration of SO2Cl2. Okay. Right. So and we have to find out concentration of SO2Cl2 at T that we want to find out. So it's very simple. So let us consider the initial concentration equals to 1 to 1, ratio of 1, or you can also define it as 100 also can. Alright, so for the initial, okay, as for the concentration of SO2, Cl2 at T that we want to find out, we needed the balance. So 100 minus 5%, so you can get 95%. Or also you can calculate 1 minus 0.05%. So that is 0.95. Okay, so for example, like this. Okay, concentration of SO2Cl2, the initial is 1 ratio, in form of ratio. Okay, over concentration SO2Cl2 at T is 0.95. So make sure you choose only one, whether in ratio or in percentage. Okay, and then substitute the value of T. Okay, T is already given 7.75 minutes. Okay, 6.75 minutes. So from here we'll get the value of K is 7.6 times 10 power negative 3 per minute. Okay, right. Right, next specify the half-life for the decomposition. So you can use directly the formula of half-life for first order. Okay, T half equals to ln 2 over K, and then substitute the value of K that we already calculate, and we get the T half or half-life for the decomposition is 92.2 minutes. So now we move to the second order reaction. Let us consider the reaction concentration A produce product. So rate is equals to K concentration A power of X. For the rate law, rate is depend on the concentration of reactant raised to the second power. Okay, so meaning that we have rate equals to K concentration A power of 2. Okay, when we substitute the unit of rate, okay, molar per time, and also the unit of the concentration of A, that is molar. So we'll get the unit for K. Okay, for second order is, when we plot graph rate law for the second order, usually we will get two kind of graph. So the first graph is rate versus concentration A. We will get here a curve graph. Rate here is equal to Y. K here is equal to M. And concentration A is equal to X squared. So graph of Y equal to MX squared, quadratic graph. Okay, start from the origin. Okay, so if you want to get linear graph, then we can plot graph of rate versus concentration A power of 2. Okay, so rate is equals to Y, K equals to M, concentration A power of 2 is referred to X. Then you will get a linear graph, Y equal to MX, start from the origin. Alright, so now we move to the integrated rate law. So when integrate both of the rate law equation. So we get this expression. Okay, A naught is initial concentration of A, and A is referred to the concentration A remain after T given time. So K is rate constant. So there are two graphs involved for the integrated rate law. So the first graph, if we plot 1 over concentration A versus time. So 1 over A, concentration A is equal to Y, equals to 1 over concentration A naught is C, okay, plus K is equal to M, gradient, and X is equal to, T is equal to X. So Y equals to MX plus C, so then we get linear graph, okay, positive with positive gradient. Okay, for the second graph, if we want to plot a graph of 1 over concentration A minus 1 over concentration A naught versus time, so this is referred to Y, and K is referred to M, and T is equal to X. So we get a linear graph start from the origin with positive gradient. Alright, next we move to the half-life. If we substitute T equals to T half and concentration A equals to concentration A naught over 2 into the integrated rate law here, so we will get this expression. T half equals to 1 over K concentration A naught. Okay. Alright, so for the graph for the half-life, we can plot concentration A versus time. Okay, and then refer to the trend. Okay, half of the initial concentration, so is somewhere here. So when we refer here, we will get the half of the concentration, the time taken is X. Half of the second half-life, so we get the time taken is 2x, and then the third half-life, okay, we get 4x. We can clearly see that the trend of the half-life, time taken for the concentration to become half is not constant. Okay, it's become double. So therefore, this is referred to the order of reaction is the second order. Now we move to the example number 5. Okay, ammonium cyanide NH4NCO in water rearranged to produce urea, a common fertilizer. This rearrangement is second order. It takes 11.6 hours for the concentration of ammonium cyanide to go from 0.25 molar to 0.0841 molar. So what is K for the reaction? So we have here is the initial concentration, and then here is the final. Okay, and then we have T here. So therefore for A here, you have to use the integrated rate law for the second order. And remember, you have to change the general equation into its specific, where A here is equal to the ammonium cyanide. Okay, substitute the values. Okay, right, and we get the K value is 0.6803 per molar per hour. Okay, for B, what is the half-life of the reaction when ammonium cyanide is 0.1 molar? So for B, you can use the formula of half-life for second order. So remember, you have to substitute A with the formula of cyanide, ammonium cyanide. Just substitute the values, the value of K and also initial concentration. Then we get the half-life of the reaction is 14.7 hours. C, how fast is referred to the rate. How fast? K is 0.839 molar solution being changed to urea. So therefore, you have to use the rate law. Okay, rate is equal to K, concentration NH4NCO power of 2. Substitute the value of K and also the concentration. Then you will get final answer 0.4789 molar per hour. Okay, so these two you have to substitute the values. Okay, next example number 6. The decomposition of nitrosyl chloride. So we have here nitrosyl chloride is second order. So it takes 0.2 minutes to decompose 15% of 0.3 molar solution of nitrosyl chloride. What is the K for the reaction? Right, so this is referred to T, and then this is referred to the initial concentration, So initial, and then we have to find out. This one is decomposed. So we have to find out what is the concentration nitrosyl chloride at T equals to 0.2. So this is the initial concentration. So for the concentration of NOCl at T equal to 0.2 minute, so we have initial concentration minus changes. So this one meaning that here should be the balance, or the remains. The concentration remain or final concentration. That is 0.255 molar. Substitute into the integrated rate law equation. Okay, so this is refer to 0.255. Substitute. And we find out the value of K is 2.941 per molar per minute.